Hello again, wonderful AP chemistry students. In yesterday's lesson, we learned about what entropy is. So today we're going to talk about how entropy and enthalpy, which is the heat of a reaction, kind of play together. So the first thing to know is that all systems, basically all chemical reactions, want to proceed to the lowest energy level. They want your change in enthalpy to be negative. They want to release heat. So generally speaking, one of the driving forces of chemical reactions is releasing energy. Systems also want to increase entropy. So, anytime you have a reaction where it's exothermic and entropy goes up, think about, for example, an explosion, or think about a campfire where you start with half of the material you start with is the solid wood plus the oxygen. You end up making carbon dioxide and water vapor plus releasing heat. That increases entropy and it releases heat. So that's a great thing. That's always going to happen. The opposite of that, the water vapor and carbon dioxide reassembling themselves into oxygen and and a bunch of wood, that never happens. Now, the question is what happens when you have reactions where you do one of these things but not the other? For instance, it's a reaction that is exothermic but decreases entropy, or it's endothermic but increases entropy. Well, that's when we need to look at something called um, Gibbs free energy. But first of all, I'm going to talk about the term thermodynamically favored. That means a reaction that once you get it started, it just keeps going. Like uh, you light a match, and the fire keeps going until all your reactants are consumed. The opposite of that is a non-favorable reaction. For instance, baking a cake requires constant input of energy. You can't just pop the cake in the oven for a second to heat it up and then pull it out and it will bake itself. The term spontaneous is uh, discouraged by the College Board. They don't like us to use that term. Um, Thermodynamically favorable or unfavorable are the terms that we want to use. So that brings us to something called Gibbs free energy. This is a way to quantify the interplay of entropy and enthalpy. And Gibbs free energy is essentially the energy that is available to do work. It's the usable energy. Because in all reactions, some you're going to end up dispersing energy into a useless form by increasing entropy of the universe as part of any process that happens. And so the question is, after you've done that, what's left? Do you have an amount of energy left, or are you going to have to source it from somewhere else? So there's a very simple equation. It's on your reference tables. It says that delta G equals delta H minus T, that would be your temperature in kelvins, times delta S. And a reaction is spontaneous or thermodynamically favored if delta G is negative. So keep in mind, if we look at this equation, if H is negative and S is positive, multiply S by your temperature, which in kelvins is always positive, and then subtract it, G has to always be negative. If H is positive and S is negative, G would always be positive, and it would be thermodynamically non-favored. So the thing is, if both of these things are positive, if it's endothermic and increases entropy or exothermic and decreases entropy, well, then whether the reaction is favorable or not depends on your temperature. There will be a temperature at which delta G is zero, which means it's neither favored nor unfavored. And at a temperature above or below that, things will change. I also want to refresh your memory about what these little degree signs mean. We talked about this briefly with thermodynamics way back several units ago. That just means standard conditions, which means if it's a gas, it's 1 atmosphere pressure. If it's in a solution, it's 1 molar concentration. And it's in whatever state of matter is most stable at 25 degrees Celsius. So we're comparing apples to apples and oranges to oranges. there are charts of standard entropies and standard Gibbs free energies of formation and standard enthalpies of formation in the back of almost any chemistry textbook. Um, so the last thing I want to show you for today about how we're going to analyze this is talking about thermodynamic versus kinetic control. So what this is saying is that there's a lot of processes that may be thermodynamically favorable, but you never see them actually happen. And those are said to be under kinetic control. In other words, the rate of the reaction is so slow or the activation energy is so high that even though it's theoretically and mathematically a favorable process, it never happens. Um, One example of that is diamonds turning into graphite. Uh, that would be a process where a diamond is a much more ordered three-dimensional structure than graphite. It's lower in energy. Gibbs free energy change is negative, but this reaction never happens because those covalent bonds in a diamond are so strong that the activation energy is enormous. So diamonds don't just decompose back into graphite. Uh, Tomorrow we'll learn a little bit about the relationship between Gibbs free energy and the equilibrium constant, and then we'll dive into our last little unit, which is electrochemistry. But I'm going to show you now a problem that occurred that was on an actual AP exam before. Let's see. So this problem appeared on an actual AP exam in 2016. And so it says, for instance, we'll focus on part D. It says, in thermodynamic terms, a reaction can be driven by enthalpy, entropy, or both. Considering the flask gets cooler as the reaction proceeds, what drives the chemical reaction? Answer by drawing a circle around one of the choices below. Well, since it gets since the flask gets cooler, that means that's an endothermic reaction, which that's not favorable. So this is not being driven by enthalpy. Uh, but if we look at the reaction up here at the top, we start with something that's solid and something that's aqueous, and we end up with something that's aqueous, a liquid, and a gas. We've produced a gas. We no longer have a solid. We move to things that are higher in entropy. Definitely entropy is driving this reaction. So you would circle the entropy only. And then you would justify your selection in terms of delta G. Well, for the reaction to happen, which this reaction does happen because it says up here at the top, the student observes the formation of bubbles and that the flask gets cooler as the reaction proceeds. So since the reaction happens, delta G is negative. And so to justify this selection, you would say, well, since delta H is positive, that's not contributing to G being negative. But since S is positive, according to delta G equals delta H minus T delta S, that does contribute to it. So it would be a valid justification for that. So those are some scoring guidelines that for how an exam would work for this. There's a few different ways to answer this, but that's just one example of type of question you could see on an AP exam. So we'll be back tomorrow with some more.